In our previous geoscience episode, I explained the mineralogy and geochemistry of celestite, but I had also briefly spoke on the geochemical makeup of barite. And so in this geoscience series, I will be delving a little deeper into the mineral crystal called barite. I will also point out the various similarities and differences in terms of the mineralogy and geochemistry between barite and celestite in this episode. I will then explain the geological processes that created both of them, but first it is very important that I tell you the origin of the word barite and its industrial uses. The word barite comes from the Greek word baris, which means heavy, which is a reference to its high specific gravity, which is about 4.5. This high density is due to the barium ion, which has a larger atomic mass. This high density makes it an excellent weighting agent in applications such as oil and gas drilling fluids. Its high specific gravity is exceptional for a non-metallic mineral, and it also remains inert and insoluble, making it suitable for use in other industries like paints and coatings. Barite is also used to block X-rays due to its high density, which makes it an effective radiation shielding material. It is commonly mixed with concrete and plaster for construction, forming high-density concrete and specialized mortars for X-ray rooms in hospitals, nuclear power plants, and research laboratories to protect people and equipment from harmful radiation. Or in other words, barite can block radiation due to its high density and barium sulfate content, making it effective for shielding against gamma and neutron radiation. Now, the geochemistry of barite crystals, which is barium sulfate, BaSO4, involves analyzing its major, minor and trace element composition and isotopic signatures to understand the conditions and sources of the barium and sulfate fluids to which it precipitated. Common sources for barite includes hydrothermal fluids mixed with seawater, cold seeps and basin brines. Barite can also be found in sedimentary rocks, clay deposits, marine deposits, and cavities. Isotopic analysis of sulfur, oxygen and barium along with trace element patterns like rare earth elements can reveal the fluid origin, formation, as well as temperature and track changes in seawater chemistry. Notice the diagram showing the geological processes that occur in an oceanic basin, such as hydrothermal activity driven by volcanism occurring at a mid-ocean ridge where oceanic plates diverge or split apart, which is the ideal environment where barite crystals can form in, or in other words, barite crystals can form from hydrothermal activity at divergent oceanic plates where heated seawater is forced through fissures in the oceanic crust. The crystals are a major component of many hydrothermal vent systems, acting as a key structural mineral in black smoker chimney and massive deposits. So what occurs is that hydrothermal activity creates barium-rich fluids that mixes with sulfate-rich seawater, causing the barite to precipitate out of the solution. Or in other words, when barium-rich fluids mixes with cold seawater, the barium sulfate in the solution precipitates out, forming barite crystals. Barite can also form on the seafloor from fluids rich in dissolved barium expelled during cold seep events, often linked to anaerobic methane oxidation, and as stated before, barite can also precipitate from high temperature and high salinity hydrothermal fluids. Now, how does barite crystals start to grow? Well, it starts first through the process of atomic nucleation, which is the initial formation of a stable crystal nucleus from a solution containing barium and sulfate ions. This process is driven by supersaturation, where the solution must exceed a specific saturation threshold for nuclei to form within the solution, which is homogeneous nucleation, or on a foreign surface, which is heterogeneous nucleation, which is more common and can be influenced by factors like pH, the presence of impurities such as strontium, and surface properties. Now, once a stable nucleus forms, it acts as a template for further growth. Additional barium and sulfate ions from the supersaturated solution attach to the nucleus, causing the crystal to grow larger. So now, what are some crystal habits of barite? Well, barite crystals commonly form in tabular or bladed habits, appearing as thin plates or knife-like shapes, often in divergent or crested groups forming barite roses or desert roses. It can also be prismatic, like a stout prism, equant or equidimensional, or rarely elongated. Aggregates can be massive, granular or fibrous or concretionary, and in some cases the crystal exhibits an earthy appearance. But it goes even further, because barite can also be stalactic, stalagmatic, fibrous, concretionary, or massive. It is also important to note that barite crystallizes in the orthorhombic crystal system. This system is characterized by three mutually perpendicular axes of unequal length. Barite is also a common mineral in lead-zinc veins. Now, in the previous geoscience series, I spoke about the geochemistry of celestite, but I did not mention its hardness level. Well, that is because both barite and celestite have a hardness of 3 to 3.5 on the Mohs scale of hardness, making them quite soft minerals. This means they are both harder than copper but can be scratched with a steel or nail. Another key similarity is in their chemical composition, because celestite and barite are both sulfate minerals, and they form in and require similar geological environmental conditions to grow, such as sulfates in marine settings, and can replace evaporite minerals like gypsum. However, the key difference is that celestite requires environments with a higher strontium to barium ratio, while barite requires a higher barium to strontium ratio for precipitation to occur, and both can be also formed in hydrothermal and biogenic environments. Another important thing to note is that barite has a vitreous to pearly or resinous luster, and the color of barite varies because even though it is most commonly white or colorless, it can also be tinged yellow, blue, red, brown, green, pink or gray, depending on impurities like iron or organic material. So what have we learnt so far? Here is a brief review and a little more information on the geochemistry of barite and how it is formed in the natural geologic environment. Firstly, barium is a heavy metallic element due to its high density, which is why barite is so dense. However, it is very important to remember that barite, which is barium sulfate, a compound of barium, sulfur and oxygen, is considered to be a non-metallic mineral. So now, in order for barite to form, we need a source of barium ions and a source of sulfate ions floating in the same fluid like water. Now, how do they come together? Well, just imagine you're making rock candy. Dissolve sugar in hot water to make a supersaturated solution. As it cools or evaporates, sugar molecules latch onto a string, forming crystals. The formation of barite is very similar. Groundwater or hydrothermal fluid becomes supersaturated. When a barium ion and a sulfate ion bump into each other, they stick because of their charges, forming a tiny, stable seed of barite. This is called nucleation. Once that first seed is there, it acts like a magnet for other ions. They attach to the growing crystal, but not just anywhere. They lock into a specific repeating pattern called a crystal lattice. This ordered structure defines a crystal and gives barite its flat-sided, blade-like shape as well as other crystal habits. Over thousands to millions of years, with a steady supply of barium and sulfate ions, the crystal keeps growing, molecule by molecule. I hope you enjoyed this geoscience series, and remember to click the like button, share the video and subscribe to the Soil Mineralogist channel, and click the notification bell if you have not yet done so. The mineral crystal up next for discussion is tourmaline, so look out for that geoscience episode.